Good evening, everyone. So today we'll start our discussion on chi-square. So in our initial lectures, we have been talking about descriptive statistics, probability, the introduction to inferential statistics. Now I want to go into the inferential statistics proper. So we'll talk about hypothesis testing and confidence interval, the type of inferential statistics we are looking at. So the first test we want to look at among the hypothesis tests is chi-square. Chi-square is a family of tests. What it means is there are many distributions that follow chi-square. It's not just one. And in fact, they call them different names in different scenarios. So we'll be looking at chi-square, Pearson's chi-square, Yates corrected chi-square, likelihood ratio chi-square, Fisher exact P. That one is not chi-square per se, but we use Fisher exact test in the situation where chi-square is not valid. Chi-square for trend, chi-square for test of goodness of fit, McNemar chi-square, McNemar, Bowker chi-square. So hopefully we'll be able to do some of them today. By Monday, we continue. So as I told you, it's very broad. Historical interlude concerning chi-square. Carl Pearson, London 1857, he was considered the founder of mathematical statistics. He developed the chi-square test, published it in July 1900. He coined the term standard deviation. So that standard deviation we talk about is the one that coined it. Developed the product moment correlation. Go to see Pearson correlation. He developed it. Now you know who to blame. Overview of standard normal deviation. Everybody know the origin of normal distribution now because we discussed extensively, especially the standard normal distribution, how it came about. So chi-square was derived from standard normal. So it's a derivative of standard normal distribution. In fact, it should have called chi-square as square normal distribution. So if you remember the standard normal distribution, we talk about the number of standard deviation and observations from the mean, which is the z-score. So you remember, when instead of you stating the value of each person, you stating in terms of how many standard deviation away. This value, especially h now, or weight, how many standard deviation away is from the mean. So that number of standard deviation away from the mean is the z-score. And the z-score, how do you calculate it? X, the weight or the value minus the mean over standard deviation. So, and it gives you standard normal deviation, normal curve. And the mean is 0. The area under it, the graph is 1. You know all those other things, mean, mode, and median are the same. So you also know that within -1 to +1 standard deviation, 68% of the observation line. Between -2 and 2 standard deviation, 95.5% of the observation line. So between -3 and +3 standard deviation, 99.9% of the observation line. We also know that between -1.6 to +1.6, 1.96 rather, from -1.96 to +1.96 standard deviation, in 95% of the observation line. Those are the characteristics of standard normal curve. So this intelligent normal curve, what he did was, if you look at the standard normal curve now, to the left side of the 0, you think it's negative, -1, -2. To the other side of the right side is positive. What it means that the positive one, they are above the mean. That's One is the number of standard deviation above the mean. The negative one is the number of standard deviation below the mean. This intelligent man now score all these minus, plus, minus, all, square them. You know that when you square something, the negative will clear. Because minus 3 times minus 3 is 9. Minus 2 times minus 2 is 4. Minus 1 times minus 1 is 1. So if you look at it now, if you square it, all those ones that is minus 2 and plus 2 originally will become the same. The one that is minus 3 and plus 2, both of them will have the same value when you square them. The same thing with 1 and minus 1, they have the same value. So it will give you something like this. This chi-square distribution. So if you look at it, they have already cleared negative out of it. So you can always start from 0. You know, the standard normal curve, you have 0 in the middle, to the left negative, to the right positive. But in chi-square distribution, after you have squared that standard normal distribution, negativity has been cancelled. You can always start from 0 and look at the shape of it's always skewed. Chi-square is always skewed to the right. Always skewed to the right. That's just the logic. So you can see what the person did. So no negative value. So now the standard deviation increases as the degree of freedom increases. So the chi-square curve spread more as the degree of freedom increases. So the more the degree of freedom, we'll talk much about that, the more the chi-square spread. So properties, it is not symmetrical, as you can see, it's skewed. It ranges from 0 to infinity, no negative value. Skewed to the right. Total area under the curve is still 1. Any probability distribution curve, this total area is usually 1. Just like the normal distribution is 1. Even the T distribution is 1. So family of distribution, that is the family, the different chi-square distribution for each value of the degree of freedom, depending on the degree of freedom. So for each degree of freedom now, 1, 2, 3, they have different shapes. So 3 has different shape from 2 plus 1 and 4. So the shape of the chi-square depends on the degree of freedom. The test utilizes a contingency to analyze data. So you got to talk about the contingency table later. The table where you have row and column. So we also call it cross tabulation. Degree of freedom for the chi-square is usually number of row minus 1 times number of column minus 1. We have already said that it's using contingency table. The table are arranged in row and column. So the degree of freedom is number of row minus 1 times number of column. Look for example here. Look at this. You can see when we talk about least form of configuration or cross or two-way table. So you see employment, non-employment, and female. So when we talk about number of cells, is the green one, the one is no, because all those other ones include that is total. So it's the total. Look at 90 plus 40 is 130. 95 plus 75 is 140. 90 plus 95 is 180. 40 plus 75 is 115. So the total is 300. Whichever way, either you say 185 plus 115 is 300, or 130 plus 170 is 300. So the periphery, those blue areas, they are the number of cells here is 4. So look at the second one. The number of cells is 3 times 4, which is 12. Number of cells, that green area is the number, is the number of cells. So you present the distribution of two categorical variables. You know, we already said chi-square is for association between two categorical variables. That is, compare proportion between independent groups. Look at it now. In this sense, what they want to compare is employment status as the outcome and sex as the exposure. This second one is socioeconomic status as the outcome, level of education as the exposure. Now, the categories for one variable appear in the row, and the category for another variable appear in the column. Look at it. For sex now, the category appear along the row because that's the exposure. So normally, just know that exposure is usually along the horizontal. The outcome is along the vertical. That is the convention. But sometimes some people do it the other way for one reason or the other. But that you may not be confused. The standard. Along the row, exposure, along the column, outcome. Each variable must have 2 or more categories. So you cannot do any if, like, for example, now they say sex, and it's only the women that are going for antenatal. So that shows that there is no man among them. You cannot calculate cancer. If you do that, even if you have a pregnant employee, there's no male. So you just have 95 and 75 with 170. So until the simplest contingency table is 2 by 2, 2 row, 2 column. So each row and each column must have at least 2 categories, 2 or more categories. If one has one category, cannot calculate chi-square. So now there are many test statistics that follow chi-square, as I've said. The one that is used to test association between 2 categorical variables is Pearson chi-square. It assesses whether an association exists between 2 variables by comparing the observed pattern with the expected pattern. When you say observe, what you see, expected, what the pattern you expect, if not hypothesis is true. Let's see, go to understand better. Different type of chi-square statistics. Pearson chi-square used for comparison of proportion between dependent group, testing of goodness of fit. No, we have said it for the first day. Likelihood ratio of chi-square is the same thing. It's only that different way. Least likelihood ratio uses logarithm to calculate chi-square. So when you calculate for the same data set, if you calculate, you calculate both Pearson and likelihood ratio, the value will just be different. I think one you see, one is a little higher than the other. Small. So, but most of the time we use the difference is not usually much. McNeman and McNeman-Bowker. So McNeman, comparison of proportion between peer group. No peer group, we have said it yesterday. When you do something, you collect your data from a group and you come back for the same people, you collect again. That's peer group. So when you are summarizing as categorical, I want to know the association, that is McNeman. So if it is only categories, there are 2. Use McNeman. But when you have more than 2 categories, 3, 4, you use McNeman-Bowker. Chi-square for trend is for comparison of proportion among ordinal group, age group, socioeconomic status, social, yes, even education status. So when you are trying to compare proportion, maybe employed, non-employed, among people of different educational level. So educational level is ordinal. So you want to see how does it change? How does the employment status vary with different occupational educational level status? That's chi-square for trend. Mantel-Ensing chi-square. For stratified analysis, that one. In the situation where you want to do stratified analysis, that's the chi-square that the statistic that we use. What statistics are the statistics for logistic regression? We still go do logistic regression. When you do logistic regression, it's using chi-square. And that chi-square is called Ward statistic, Ward. Well described by Professor Ward. Krukawali statistics. Non-parametric statistics for comparing more than two means. Then we have, you remember, let's say when you do ANOVA, the non-parametric counterpart is Krukawali. That Krukawali is a form of chi-square. Lagrange statistics for comparing Kaplan-Meier survival analysis. This was just for academic purposes. You don't have to bother yourself. So requirement, we deal more on Pearson, Guinness, Fit, Trend, and Lemma. All those other ones, they don't concern us. Requirement, you must have two categorical variables. You must have two categorical variables for you to. So that is why chi-square is for association between two categorical variables. Two or more categories. You must have more than one category. Sex, male, female. And not just say sex only female. Cannot work. Independence of observation. There is no relationship between subject in each group. The categorical variable is not clear in any way. No. This one now is not applicable to McNeema. It's just generally for Pearson chi-square because, as we remember yesterday when we were talking about assumption for using parametric test. So I see some requirements are not so important, especially that pair or no pair, dependent or not dependent. So it's the same thing here. So relatively large sample size. You must have large sample size. If your sample size is very small, your chi-square will not be valid. Especially if the chi-square is very small and the number of categories of the outcome is small. For example, come and pick your mommy's spoon. So, two categorical variables. Okay, relatively large sample size. If the categories are plenty, for example, when you say, for example, now level of education, about 4, and you want to calculate with another one, which is maybe socioeconomic status that is about 3. So if you calculate, you are going to have 12 cells, 4 times 3. So if the sample size is very small, so in some cells, you may have scanty number. So expected frequency should be at least 5, majority, 80% of the cell. I will explain this one later. So the number of independent pieces of information that go into the estimate is the degree of freedom. So in chi-square, the degree of freedom is calculated by row minus 1 multiplied by number of column minus 1. Look at this one. The meaning of the degree of freedom here. In this cell now, you have 4 cells. How many can vary? How many you can vary in the value? For example, now, if you say you change 19, you cannot change another one. Or if you change 40, you cannot change another one. Because, we have 19, 40, 95, 75, and they already have total, both horizontal and they already fixed. If we change any value to maintain, for this 2 by 2, there's only one you can change. It's only one set that can vary. For example, now, if this 40, instead of putting 4, you just put 35, that shows that 19 will become 95. Because for you to add up to 130. That shows that 75 will become 80. For you to add up to that 115. And you see now, so you cannot change, it's only one value that can be, that's the degree of freedom. It can be any of them, but you just, whether just put red 9, just say 1, degree of freedom is 1. When you are dealing with 2 by 2 table. When you are dealing with 2 by 3 table, you have 6 cells, the degree of freedom is 2. You can see it occurs in 2 ways. That's why I put 2 ways. The first one you may have 3 column, 3 row, 2 column. Or this other one, 2 row, 3 column, whichever way. Because if we, for example now, if we vary A, you can see vary because if they put total, if you vary A, you can see vary another one. You can only vary 2. If that's why when we are asking you questions, sometimes to complete the table, they give you the total, and when they ask the question, you use this logic to fill in the table. If they already give you the total around those blue area, so you put in value. If you know value of any of them, for you to complete the whole table, you must know value of at least 2 cells. So the degree of freedom is 2 here. Remind you, as we are doing it, this first one is if you say row minus 1 times column minus 1, 2 minus 1 times 2 minus 1, making 1 times 1, 1. Can you see? So if you say 3 minus 1 times 2 minus 1, that's 2 times 1. That's 2. The degree of freedom is 2. Or 1 minus 1 times 2 minus 1, 2 times 1 is 2. When the degree of freedom is 3, in this situation, you may have 2 row, 4 column. 4 row, 2 column. So you need the degree of freedom is 3. For you to complete the table, you must know the value of 3. So the degree of freedom is 3. And if you look at it, 2 minus 1 times 4 minus 1, that is 3 times 1, 3. When the degree of freedom is 4, look at it. It comes in 4 ways, 3 ways rather. 3 column and 3 row, 3 column, or 5 row, 2 column, or 2 row, 5 column. And it give you the degree of freedom of 4. 3 row, 3 column, 3 minus 1 times 3 minus 1, 4. 2 minus 1 times 5 minus 1, that is 1 times 4, 4. Can you see? So the degree of freedom of 4 can come in this. The degree of freedom of 5 can come in 2 ways. 2 row, 6 column, 6 row, 2 column. So that situation, 2 minus 1 times 6 minus 1, that's 5. The degree of freedom 6 come in 4 row, 3 column, 3 row, 3 column. No, it's not 3 column. Sorry. 3 row, 4 column, 2 row, 7 column, and 7 row, 2 column. All of them give it to us. So it's like that, continuing like that. Now, having know the degree of freedom, we have already said the degree of freedom determines the shape. So each degree of freedom has shape. Look at it. All this graph. This red one now, the degree of freedom is 1. Look at the way the graph is. When it is 2, when it is 3, when it is 4. That's the shape of the normal I-square. Look at this one when the degree of freedom is 5, 10, 15. Look at this when the degree of freedom is 1, 3, 15, 31. Who can tell me, as the degree of freedom increases, what do you observe? As the degree of freedom increases, what do you observe? So please unmute that talk. This is a workshop. We're supposed to talk. As the degree of freedom increases, what did you observe? Nobody.
The graph is becoming more flat.
Yeah.
Who is talking? Mercy, we cannot hear you. Mutar says flat. Becoming more flat, but there is the flat you observe there. What is the
of the graph is reducing?
What happened to the shape? It
The
look like
distribution shape is changing. It's becoming more pure.
It's becoming more symmetrical.
Yes, more symmetrical.
Becoming like normal distribution. As the degree of freedom increases, the chi-square begin to look like normal distribution. All those distributions that are like, even T, even F, as the degree of freedom increases, they begin to look like normal distribution. We already said that it's normal distribution that is behind each of those distribution. Look at it now. Chi-square was derived from normal distribution. As the degree of freedom increases, it begins to look like normal distribution. Thank you. The critical value for the degree of freedom. Now, what we mean by the critical value here is that if you remember our normal distribution, we usually have our middle 95%, where 5, we have 2.5 on the other. That in the graph, we have the middle 95. We now have 2.5% on the other side, 2.5% on the other side. Because this one is not symmetrical, I've already said it. Since it's not symmetrical, the usually one tail, that is one side we look at. If you look at it, if you set your we have done special statistics, your degree of the level of significance, set it at 0.55. 0.005 rather, 5%. Now, at what, if you read that chi-square from a 0, at what value of chi-square with area in the graph be 95% of the total area? That level is the critical value for the chi-square. That level where the area is 95%, it now remains 5% on the other side. So, and that value of chi-square at which the area on the left is 95%, while the remaining 5% is not the same for all the degree of freedom. So for degree of freedom 1 is 3.84. Look at one down for the degree of freedom. Which ones no? Is it degree of freedom 6 now? Yes, 6. The value is 12.23. For different degree of freedom, it has different critical value. And that's why, if you remember, you that did MPH, you know that I give you this table, chi-square table, to check. So can you see? The green area is in 95, the blue area is 5%. So that's it for the degree of freedom of 1. So we are talking of 2 tail now, test. If you are 2 tail, so when we have 95% green, 5%, which is 0.05 blue, you see the degree of freedom 1 is 3.84, the critical value. For the degree of freedom 2 is 5.9191. For the degree of freedom 3 is 7.815. So the degree of freedom determine the critical value for the chi-square. So how do you now use it? Give this one. Let me just, normally I just put this formula, not for you to cram the formula. If they say calculate chi-square, the chi-square formula usually chi-square is equal to sigma. Sigma means addition of observed value minus expected value square over expected. Now let's talk about, for you to understand it from, let's talk about what is observed value, what is expected value. So, for example, the first example now. It's better you do example. So when we do this one, we run it. Naturally, we have the data set with us. Now, look at that employment status and sex. So we have 300 people, 130 male, 170 female, 185 employed, 115 not employed. Everything is still on there. So the contingency table now is 2 by 2. So the cell is 19, 40, 95, 75. Those 19, 40, 95, 75 they are the observed frequency. So that's what we see. When you did your study, when you do the, you say, 90 mil, 40 mil. The out of the 125 now. So that 90, 40, now the
Sorry, your mic.
Yes?
Your mic. You're sounding
Okay,
far from
sorry.
the phone.
Yeah, I think it's an angle. I was sitting at an angle. Oh, from when? From when? So that I can repeat.
You're talking about the employee that is 90 and they're not employed
Okay.
as 40.
So what I said as this table you see, the 90, 40, 95, 75 are the observed value. Those are the things you observe. That is 19 mean out of the 130 women, men, male, 19 employed, 40 non-employed. Out of the 170 female, 95 employed, 75 non-employed. Or you can say in another way, out of 185 that are employed, 90 are male, 95 are female. Or out of the 115 that are not employed, 40 are male, 75 are female. Now, if they ask you, who is more employed? What will you say? You can unmute and talk. Who is it male or female that is more employed?
It's female.
Who is more employed?
Female from the observed value.
Female are more employed?
Yes, sir.
Okay. Let's see if it is true. Now, we shall see if it is true. Now, if you put 90 employed male divided by 130 times 400, what does it give you? You can do it now with your phone. 95 over 170 times 100. 90 over 130, that is 90 out of 130 female. What's the percentage of employable? Do the same thing for female. What did you get? What did you get? It's practical session, so that's why it's not just to be talking to the air. So what did you get? What percentage of male employed? No answer.
From the calculation is 80.166.
What percentage of male are employed? What percentage of male are employed?
69.2.
69.2. I don't know. It's arithmetic. Okay, what percentage of female are employed? What percentage of female are employed? No answer. 95 over 175 times 100. What percentage of female are employed?
55.88, I think.
889. So you can see that more male are employed. Because you don't just look at the figure, because you see that 90 male employed, 95 female employed. 90 male out of 130. The number of male, they are fewer than that of female. We have 170 female and 95 are employed. We have 130 male, 90 are employed. So employment rate is higher among the male than the female. Does it make sense now? So this 90, 40, 95, 75, that is the difference from the percentage we have said. That is the difference we have seen that it appears that more male are employed than female. But is this statistically significant? Is it this different? Is it due to chance? What the percentage? What is the probability that this difference is due to chance? So for you to do that, you need to calculate what are the values that are supposed to be there. If let's say no hypothesis is true, and no hypothesis say there's no difference in the employment rate between male and female. That's what no hypothesis say. So if there's no difference, what should be in all those cells? Those four cells, instead of 90, 40, 95, 75, what should be there? So intelligent people look at the table now. That's okay. The expected value for May should be 130 over 300 because May constitute 130 of the 300. 130 over 300 times 185 of the 300. So that is what is telling me that 130 over 300 of the 185. What does it give you? So it will give you 80.17. That is, this is the number of May that's supposed to be there if there's no different employment rate between male and female. If you look at the female on down, you can see since female constitute 170 out of 300, 170 times over 300 of that 185 give you 104.83. That will be the number of the female that should be there. You know, it's because of calculation. That's why it's not giving whole number. Actually, if you want to approximate, this one will be 105. Now, it's the same thing you do for the people not employed. So if 130, we have 130 May out of the 300 times 115 or unemployed. So unemployed, the number of female May unemployed should be proportional to the contribution of the male. So when you do it now, it should give you 49.83. The same thing for female, it will give you 65. So this value, 80.17, 104.83, 49.83, 65.17, these are the expected value. That should be in those cells if there's no difference in the employment rate between male and female. If you want to confirm, okay, somebody should type 80.17 divided by 130. What does it give you? 80.17 May over 130. Because the total May is 130. What does it give you? Yeah, do it. And you do it for female.
$0.61.
0.62, let's say 62 approximately. Which is 60. We can even call it 60%. Percentage 61.7. 61.7%. Okay, let's do for the female 104.83 divided by 170.
$0.62.
61.7 the same. Can you see now? So like I said, if you have put the expected value there, the proportion of female that I employ and male that I employ are the same. Does it make sense? That's the expected value. That's the values that should be there if the proportion of male and female that I employ are the same. And the proportion of male and female that are not employed are the same. But if you calculate for the non-employees, they give you the same thing. The same. So you put in the formula is expected, and the formula is sigma summation of for each of the cell observed and expected, square it over expected. You do it for all the cells and add together. That is the chi-square, 5.5353. And we know that the critical value for chi-square at degree of freedom 1, because this one degree of freedom 1, 2 by 2 table, is 0.05 level of significance, is 3.841. Therefore, the chi-square of 5.553 is statistically significant because it's far, far higher than the critical value. That shows that there's a difference in the employment rate between male and female, where we find out. And the difference is not just due to chance, because the probability that is due to chance is less than 0.05. Is there any question? So somebody should, now let's run this one. Somebody to share socioeconomic status. Open your express and open that. So if you can just go to where you store the data that I give you, you don't even do open express. If you double click on that express document, socioeconomic status, it will open the express for you and open that thing. So somebody should do that and share. So let's run this data set here. Let's run it and see the way it is. SPSS. So who is doing that? Who is doing that?
Okay, sir.
Okay, Mercy, you want to do it?
Sir, you're the only person that can check.
Okay, sorry, sorry. I've opened it. Yes, socioeconomic status, yeah. If it's open for you there, we will not see it. So you have to stop sharing and share it because we are just seeing where the data are. So if it is possible it has opened for you, stop sharing and now share that one.
Okay, sir. It hasn't opened yet.
Oh, it has not opened, okay. That's your computer, the RAM is very small.
Maybe. But it's going to open up.
That's open.
No, it's loading now.
If you just right click, you'll have right click and open. But if you double click, sometimes the thing may not click it. And you think, yeah, it just be rooming.
Okay, that's opened.
Okay, yeah. Stop sharing and unshare that one. Go, you can't see it. Stop sharing and share again. You now look for that one.
Okay.
Yeah. So you go to analyze. If you look at it, the sex is there, employee is there. For after age, you see serial number, age, sex, employment. Okay. Go to analyze. If you look at it, we have entered the sex. Maybe one mean male, two mean female, but it's already there. The employment. So just go to analyze.
Okay, sir.
Then cross tab goes to descriptive statistics. Descriptive statistics. Cross tab, you see cross tab. Number 4 on the row.
Okay.
Cross tabs. Yeah. To move the sex to the row. You know, I've told you the exposure is along the row. Sex to the row.
Okay.
Employed to the column. Click on exact. Click on exact. Or, you know, if you see by default, it choose asymptotic only. We have Monte Carlo, but click on exact, the one down. Exact.
Okay.
Okay, continue. Click on continue. Click on statistics. Click on chi-square. Chi-square is the first one there. Continue. Click on continue. Continue. Click on cells. Cells. Cells, you see after the statistic, there's cells. Not sex. Cells.
Yeah,
cells. Yes.
Okay. Yeah.
Then click on, you see the percentage row. Click on row. So when you want them to give you the percentage, your percentage should be along the row, in as much that your exposure is along the row. But if you put your exposure along the column, you will now put the percentage you want to do is the column percentage. Is where your exposure variable is that will give you on the percentage. Otherwise, if you don't do that, you get wrong interpretation. The chi-square everything will be correct too, but you get wrong interpretation. So now we may even want to show expected. Click on expected so that it gives you expected value also. And most of the time, we click continue. Okay. So we then see you have to stop sharing and now share the output, the result. You are not seeing the result. Stop sharing this and share this. Yes.
Okay.
Yes. You can see. So, but the thing is crowded because of the expected value we put. You can see all the expected, you can see each value and the expected value we calculated the other time in each of those cells. You can see 1980.1, you can see 4049.8, you can see 95104.8, 7565.2. All those are the expected values. So you will see, apart from that, look at the percentage that we calculated the other time, 69.2% of May are employed, 30.8% of May non-employed. Then you have 55.9% of female employed and 44.1% of female non-employed. So scroll down to see the statistics. Scroll down. So you can see the chi-square, Pearson chi-square 5.553. That's what we calculated. You can see continuity correction. We'll come to that later. You can see likelihood ratio, which I told you the other time. You usually have a value that will slightly be higher than a Pearson chi-square. But it's different methods. Logarithm is used to calculate that. So now you will see an alert A in on the below the table. You see, is 0 cell is 0%. Half expected count less than 5. The minimum expected count is 49.83. If you look at it, in female, the male not employed is the minimum expected value, 49.8. Now, we already said chi-square will not be valid if we have more than 20% of the cells having expected value less than 5. But here now, it's only, there's no cell. That's why they say 0 cell. No cell has to. And apart from that, apart from the fact that, okay, if more than 20% of the cell has expected value less than 5, another condition is if there's any cell at all that has expected value less than 5. And that is why the people that program these SPSS, they have employed some statisticians, so which are really very clear here. For you to know if the proportion of cell that has expected value less than 5, they will give it to you there. They will say 1 cell, so 25%, 2 cell, 33%. It depends. You know, the percentage of the cell now depends on the number of cells. If you are looking at 2 by 2 table like this one, 1 cell is 25% out of the 4. 1/4 is 25%. But if you are looking at 6 cells, look at 2 by 3 table, 6 cells, 1 cell will be around 60.7%. 2 cells will be around 33.3%. Can you see? So if we are dealing with 2 by 2 table. If there's expected value less than 1 in one cell, that one is more than 20%. Because one cell out of 2 by 2 table, which is 4 cells now, is 1 out of 4 is 25%. So which is greater than 20%. So if one cell in this one, let's say we have one cell that has less than 5, observer less than 5, the chi-square will not be valid. But then if we have maybe it's 2 by 2, 2 by 6 cell, if there are 6 cells, one does you have expected value less than 5. You will see that it will say 16.7% have expected value less than 5. 16.7% is not up to 20. So chi-square is still valid. But if you say 2 cells, like 3.3% has expected value less than 5, that one is more than 20. Chi-square is not valid. For you, the other condition that even if there is expected value less than 1 in any cell, that's why they give you the minimum expected value. Once you get the minimum expected value, you'll be able to know is it less than 1. But once you minimum expected value, you have the expected value like less than 1, chi-square is not valid. There is for the less than 5%, that will be at least 20, more than 20% of the cell having expected value less than 5. I don't know if you understand this, because it's very, very important. It's not just to run analysis. You must be able to interpret the result. Any question? Any question? Okay, let's stop sharing. Let's go back to this. Let's talk about that Fisher exact and Yates correction. Thank you. So I think I've talked about all those things. Yates correction, what Yates correction is all about is that, if you look at chi-square is used to find association between 2 categorical variables. The chi-square itself is a continuous probability distribution, just like normal distribution. Chi-square is a continuous probability distribution. We say you even derive it from normal distribution. So Professor Yates believed that if you have 2 by 2 contingency table, which is very small, he said that chi-square you did is not so accurate. You must make correction. And the correction it does when you say observed minus expected, you now remove minus 0.5 before you square it. When you say observed minus expected, it's absolute different. You now remove 0.5 from it. So if you look at it with the same calculation and look at it, for everything we just remove minus 0.5 before we square. So the implication of it is that the chi-square is a little bit less than the one we have calculated, the normal one we have calculated. So now they call it Yates corrected chi-square. The value is usually small. So sometimes when you present your results, some examiners say, is it Yates corrected? Number one, you have to Yates correction is only applicable to 2 by 2 table when you have 4 cells as one. And some people believe that there's no need for that correction because you see chi-square test is already a conservative test. So all this I also believe that. Fancy that correction. I'm not telling you, some people they use it to their own advantage. For example, if like this one now, both Yates corrected chi-square and the chi-square itself, they are far, far above physical value. 2 is significant. So they will not say, corrected chi-square. If you use the Yates, it stays with you. But if the chi-square, the value is at the border, the critical value is 3.484, the graph you don't want, 3.841. Imagine if your chi-square you are corrected is around that 3.841. So, and the corrected one is less. In that situation now, because the original one is less small. So the original one is significant. The corrected one is not significant. People will choose the real one and say, look, well, it's no more significant. So we will use it to the other advantage. If both of them are significant, they'll now take the corrected high square. Some of them don't even know the meaning, logic behind it. C8 corrected. Another thing that some example also know that they don't even know that is expected value. Expected value. Normal, yes. If the number of value in the observed value is scanty, maybe small, there's a probability that expected value some of them will be less than 5. But it's not all the situation is like that. In fact, you may even see 0 in the cell and the expected value is greater than 5. So some of them, when they look at your table, they say, look at this value here. Maybe there's 4. You want to say, look at it. Only you are supposed to use the value is less than 5. You are supposed to use Fisher. No, it is the expected value. And how do you value here? That is the logical way to calculate it. The mnemonics for people who count is row total and column divided by grand total. For each of the cells, you calculate the expected value. Look at for cell 1 now. The row total, is 130. Times column total is 185. That's for May employed. Row total is 130. Column total is 185. You can see 130 plus 185. Divided by grand total. Grand total means total, which is 300. The same thing for each of them. Row total times column total divided by grand total. That's how to. So sometimes when you are in an exam, you calculate the expected value. You can put your phone and see. Expected value is row total times column total divided by grand total. So some of them, when they see some value, this thing is less than 5. It's not the observed value. It's the expected value that must be less than 5. That must not be less than 5. It's not the observed. And the expected value, so when you have maybe 6, if the expected value is less than 5 in 1, it's still valid because that 1 is 60% of the 6 cell. When you say 1 over 6, 60%, it's not to 20%. Are we together? Now, after the calculation, then there's what we call the likely. Okay, we leave this likely ratio. Okay, I think there's a place. Okay, so whenever is this I'm looking for now. Anyway, there's no need to demonstrate now. The Fisher exact. So now, if you remember, when we're running the analysis, I said you click on message, you click on exact. It will calculate Fisher exact P. Fisher exact test is not a statistical test like chi-square. All these tests, you must have a corresponding P value for each of the value of this test. A chi-square now have a corresponding P value. You know that the advance of computer make it easy. All this one we are okay. The critical value is this. That one is only in those days when there was no computer, and it's only for you when we are writing exam. That's why I give you the statistical table. But in the real life now with the computer, the computer will give you chi-square and corresponding p-value. If you solve with hand, you cannot calculate p-value. You can only calculate chi-square. You will now look at the table. This value is above the critical value because that critical value corresponds with the p-value of 0.05. Can you see? Now, the computer will give you the chi-square and give you the p-value. If the p-value is 0.006, it will give it to you. By looking at it, this figure is less than 0.05. It's significant. If it is more than 0.05, it's not significant. Can you see now? Oh, it's so interesting. So look at the Bayesian chi-square. Yes, corrected. We have done, and okay, this is here. Even the Fisher exact. So Fisher exact is direct probability. So instead of test, say this is a test, the corresponding p-value is no. Fisher exact is p-value. Fisher exact p. You just calculate the p. So when the chi-square is not valid in a situation whether either we have more than 20% of the set having expected value less than 5, or if there's anyone that has expected value less than 1, in that situation, Fisher exact will be used instead of chi-square. Chi-square is not valid. You calculate, you use Fisher exact. The calculation is regular. Nobody will ask you to calculate better. You see how to get you when you are on the analysis. You go to exact, you click on exact. So it will, even this one we did, it give us Fisher exact. It will calculate for you, but we don't need it. We usually do that so that in case we need it. Because in case alert you that way to this so less than, you will see 2 cells, like 3.3% has expected value less than 5. The smallest value is the, you already know that it's Fisher. At least you already think that it just. No, but we still calculate, we still write the chi-square at their p-value, but we now put that extra Fisher exact p for them to know that yes, because that's the one that is valid now. So the same thing, this you have to run it. The same thing, the step in running it, which Messi has done. Now let's talk about Fisher chi-square for trend. Now, let me just go. I've already told you before. Look at this table. They show the employment status among people of different level of education. Can one say that employment vary linearly along the level of education? You will see now the exposure is level of education, the outcome is employment status. No, if you see outcome is dichotomous, either employed, not employed. So for Fisher, for the chi-square for trend, the easiest must be, the outcome must be dichotomous, either the yes or no, here, there, not the employer, not employed. Then but the exposure value must be ordinal, something that has gradient. You cannot do it for religion, because religion is not ordinal. There's no need to show that one religion is superior to the other. You cannot do it for ethnicity. No. It's something like even occupation is only when you do the right classification of occupation. There's a right classification of occupation, call it registered general classification, where you say some are professional, intermediate, non-manualist skill, partially skill, and unskilled labor. In that situation, you have arranged them in order. In that situation, you can do chi-square for trade. Maybe all this education, civil service. How no meaning? Because civil service, a cleaner is a civil servant. A doctor, an engineer, accountant working in the civil servant. So when someone says civil service, it doesn't even show anything. So now, this one, the level of education, can you see the employment? You can see that at 3.3% of people with no formal education are employed, 41.2% of primary education are employed, because I put the percentage in the front, 64% of secondary employed, 86.7% of actually employed. Actually, if we didn't put the percentage now, people may think, well, we may think that the most employed will be secondary. Yes, because it's 80, while tertiary is 65. But that secondary, 80 over 125, is smaller than 65 over 75. Can you see now? That's why you must be able to know the percentage. So it's a calculating is very rigorous, not something you bother you with. That's what I calculated, how you calculate something. Yeah, eventually, it gives you, look at the and the chi-square 39.18. Now, the degree of freedom for chi-square for trend is usually 1. Forget about number of categories there. It's 1. Chi-square for trend, the degree of freedom is usually 1. So we have, let me stop sharing so that Mercy will go back and share that the data, socioeconomic status T. The data is there. Let's run it. Mercy, share the socioeconomic status. Or have you closed it? Are you there? You're on mute. You're on mute so that if you are talking. Okay, he may not be there, may be cooking. She may be cooking. Let somebody share socioeconomic status. Socioeconomic class, rather. But that's the name of the, is it class or status? The name of the data set. Nike, Ajakwe, share your own. On mute if you are talking. On mute if you are talking.
I'm not with my laptop.
See, all of you using phone. So if me, I'm using phone. Asmao, share, please.
So I want us to
Mercy.
share.
Yeah, I've been calling you. It's like you went to cook. We're calling
No,
you.
sir,
Share the same data set you shared the other time.
so is it the output?
Not the output, the real something. It doesn't really matter anywhere you see because it's
Okay.
still the same. Even if you share the output, it link to it's still the same document. Share anyone.
This is the data set.
Yeah. Now you see education is there, and we have employment, it's still the employment status we are talking about. So go to analyze. Analyze. Go to cross tabulate. Yeah. Descriptive statistics, then cross tab. Like what you did the other time. Return the sex and put education there. Yes. That's all. Go and remove, go to cells. I don't want the expected value again. Is clog the data. Go to cells. Remove expected value. Expected. Continue. Okay. Okay, you have to share. You have to share the output for us.
Okay.
Yes. So scroll down to where the statistics, all those statistics are. So all these other one, the percentage, everything, you know it. You see for the SPSS, the way it presents the chi-square for trend is linear by linear association. If you look at the value there, 39.185, that's what we calculate. We done in our calculation in the working. So is the chi-square for trend called linear by linear association. And the degree of freedom initially what? Look at it calculates ordinary chi-square like if you can you see the degree of freedom 3, but for that linear by linear, which is chi-square for trend is 1. So if you can look at the chi-square and the thing is significant. The P is less than 0.01. that show that the thing vary and is significant. The thing increases. You see, employment status increases with level of education. Does it make sense? Does it make sense? Any question?
Yes, sir.
Yeah, ask your question.
Okay, sir, for this chi-square, that means we still need that table after the SPSS for the interpretation.
Yeah, you need the table. You have to this table now. You have to paste it. This table that you have to paste it now. What is employment? Yes, no. Level of ratio, and you now put with the percentage and put it there, and now say pi chi-square for trend. You need the table now. You need to. Is the table you go to transfer to your Word document?
No, I'm talking of the statistical interpretation,
Yes,
whether it is
now.
significant or not.
That one is by the time you even see and you put p-value less than 0.01. Is when you are writing up. That's it. There is the proportion of people that are employed vary across the different level of education, and was statistically significant. P-value this. Curious something now. So it's when you are writing on that you can interpret it.
Okay.
Is it clear?
Yes, yes, sir.
Sometimes you go and carry any other one. Okay, if there's no other one, you can stop sharing. Let's move ahead. Stop sharing. Okay, thank you.
Okay, stop.
Yeah. Any question? So let's look at chi-square test for goodness of fit. So that's the one we. Okay, the way I wrote it. Well, let's just do it for goodness of fit. So a single, as I've told you before, chi-square test for goodness of fit is a single sample non-parametric test. Also refers to as one sample goodness of fit test. It's used to determine whether the distribution of a categorical variable, e.g., ABO block group, follows a known or hypothesized distribution, e.g., a known pattern in the population. The expected frequency of each group of the categorical variable can be equal or unequal. So, I was telling you the other time, was it 3 days ago? I give example of this ABO group. Imagine maybe in the clinic there, they've already known among the 9 university students that are coming for this thing, already known that this is the ABO, the percentage that for A, this percentage, B, C, and B, A, B, and O, this percentage of the blood group. And you now did a study, and maybe about 400 or 300 people, you now get your own percentage. Your percentage may not be exactly what they have there before. You want to now compare that your percentages as test of goodness of it. It's one sample now. You are just comparing your own percentage you have gotten from that one sample of yours to the percentage you have there, which they are public. And the sample, their own sample, they will not tell you. It's just to say, okay, A is in our own record, A is 15%, B is 20%, AB is this percent, O is this percent. So now, how do you do it? So look at example, the table below shows the distribution of ABO blood group in a tertiary hospital laboratory and the expected frequencies in the population. Can one infer that the distribution observed in the hospital significantly differ from that of the population? So it's very simple. It's the same way you calculate chi-square. All you know to do, let's see the way you calculate your observed value and the expected value rather. Look at the table. A, B, O. Can you see the frequency you have gotten? 76, 74, 31, 119. Then the percentage of this one, that is 76 out of 300. What does it give? 25.3, 24.7, 10.3, 39.7. Then the percentage distribution in the population, that is the one they had before, which they gave you, is 21.1, 80.9, 50.4, 44.6. So, you know, your expression frequency, your observed frequency, observed value are this 76, 74, 31, 119. Then you want to get your expected value. For you to calculate the expected value, it's very simple. So what you do, you know, they didn't give you the frequency for the one that they just gave you the percentage. So all you need to do is to apply that percentage to your own study population, which is 300. So look at the expected value now. 21.1 out of 100. That's 21.1% mean 21.1 over 100. So 21.1 over 100 of 300 will give how many? What's the count? 63.3. The same thing, 18.9 over 100 of 300. 300 is your own sample size. You are applying their percentage to your own sample size. So this one gives you 56.7. Then 50.4 over 100 of 300 give you 46.2. The last one, 44.6 over 100 of 300 give you 133.8. So you've gotten your both observed and expected value. You just calculate. Just the normal formula for the chi-square. Chi-square is sigma observed minus expected square over expected. So you do it to give you 40.46. The degree of freedom here now, you know, is not, this one is not cross tabulation now. Because this one is one sample. It's not cross tabulation, and it's just one variable. Now, so the degree of freedom is number of category minus 1. So number of categories of outcome minus 1. You know, the ABO block group is 4 categories: A, B, AB, and O. And 0 rather. So 0 or O is O and O. So is 4 minus 1, making 3. So if you look at the critical value, degree of freedom of 3 is 7.815, and you are calculated 40.464. That should that is statistically significant. So who will share? There is a data, the ABO block group. Who will share it? There's a data set there. ABO block group.
Okay, let me try.
Okay. What's happening?
So I want us to share
Yeah, somebody say you want to try. Is it Mokhtar? Yeah, I didn't say that.
is
Yeah, let's see if you
Yes,
can see.
I'm open.
You also bring your SPSS. What you'll have done was you will have gone to that where you put that. Okay, go and read it now. You can open, you can expand it, then go to File, Open, and look for where you put it. But if you have gone to where it is, just double click on it, it will open SPSS for you directly. So that one is faster. The data is not new. Open. You are seeing new. Open data. So it's ABO, yes. Open. Yeah. So you see the ABO block group is there. We put one. If we have labeled A is 1, B is 2, AB. If you go to view now, you see the labeling. So A is 1, B is 2, AB is 3, O is 4. So now go to analyze. So go to non-parametric test. It's not cross-tabulation, non-parametric test. So yes, check that legacy dialog. Go to chi-square. Click. So you move block group to that place. Yes. So you now move. You go down, you see values. Otherwise, we have expected, yes. You know, if let's say, for example, if let's say in our expected, all of them are equal. I think in our expected, that 4, that should that each of them will be 25, 25, 25. So you don't need to put, you just say all category equal. Yes, I mean, imagine now if maybe we are doing something for maybe number of the proportion of different this thing that I employ in federal civil service from each geopolitical zone. So there is a data they have that for this is the proportion for Igbo, for South, Southeast, South, all those. And somebody now collect the data and they want to compare. In that situation now, if let's say in the expected, what they have before, they say that is equal. So that will divide into 6 equal. So in that situation, you just say all category equal. But this one, all category are not equal. So you have to put the value. The first one, value, put your distance. Put your cursor inside that one, in that place. So what is the expected? You have to, what is the expected value? I think that one is 21.1. That percentage now, I will calculate it, 21.1 hard. So I'm coming. The second one, the second one, I'm trying to check it. The second one is 18.9. No, sorry. The expected, no. The expected is, sorry, is 63.3, depends on Google. The first one is 63.3. The second one is 56.7, 46.2, and 32.8. Go back. Yeah. No. Clear, because that first one is 63.3. Clear them. No. Go to all. Maybe it will clear. Go to all first. Maybe it will clear. Go to that all category equal. Click on it. Click back. Okay, didn't click. Okay, go back to value. Go back to value. Click on this icon now. Yes, and click on each of them. Click on that 21. It will remove it. Click on it. Remove. You see remove. So the first one is it's okay. The first one is 63.3. The second one is 56.7. So go, then remove, click on that something and remove that 53, delete that 63.3. Click on that place where you wrote 63.3. Oh yeah, replace it with 46.2. Hard. No, it will go. Yes, correct. Then the last one is 133.8. Okay. Yes. You can see, if you look at it now, it gives you, it even give you the exact and expected. Look at it. Chi-square is 40.464, which we got degree of freedom theory, p-value is 0.02. Any question on that? Any question? Don't like when something is cold. Many people now share. They say my computer is and they are not practicing it. Yeah. So okay, stop sharing. So let me share my own slide. So that is, we are through with the goodness of it. Then let's discuss this McNemal chi-square. If in this McNemal chi-square compare proportion between two related groups, I told you when I say two group related. Group is statistic, I told you, is not actually a group of persons, it's group of the data. Group of data. So when the group of the data, two group of data are from the same persons, they are two related group, or dependent group, or repeated or pair group. We call it repeated measure or pair observation, with the variable having two categories of outcome, yes or especially yes, e.g. yes or no. So for McNemal, is paired, and the outcome, possible outcome is yes or is either of the two possible outcomes. And if you draw, of course, if that is the case, you look at the table. Outcome 1, outcome 2. So that before, measurement before. Then outcome 1, outcome 2, measurement after. You will see the concordance are A and D. That is outcome 1 cross outcome 1. Outcome 1. D, outcome 2, outcome 2. But these C and D are the discorder. What we mean by, if you look at the example below, the table below shows the hypertensive status of a group of the adult before and after intervention that involve lifestyle modification. Did the intervention significantly influence the hypertensive status? Now, you will see that 200 people are involved. So when they measure the blood pressure and classify hypertensive and hypertensive before, if you look at it, the people that are hypertensive before, total is 60. Non-hypertensive before, the total is 140. But after, the people that are hypertensive, that's after, it's 40. The people that are not hypertensive, 160. You will see that here, the one we call A up here is the yes, is the 8. So you see, yes. The 8 people, they were hypertensive before, they are still hypertensive. The 108, they are hypertensive, they were not hypertensive before, and they are not still hypertensive, they remain there. So all those ones that didn't change, the calculation has no regard for them. The one calculation I have regard for is 52 and 32. 52 hypertensive before, but not hypertensive after. 32 non-hypertensive before, but hypertensive after. So one group change to hypertensive from hypertensive to non-hypertensive, the other one change from non-hypertensive to hypertensive. Is the change, the discordant is the change you are interested in. Now, the formula for this is actually the same. Observed minus expected over square over expected. But it's only for those two cells I've seen. Now, where will you get observed is what we are saying, 52 and 32. Expected, how do we get expected? Expected, remember expected value at the value when non-hypothesis is true. Non-hypothesis is true when you see that shows that the number that changed from hypertensive to non-hypertensive should be equal to the number that changed from non-hypertensive to hypertensive. That is when the non-hypothesis, there's no, this intervention did not do anything. There's no change. So it is when the one that changed from A to this equal the one that changed the opposite direction. That's a no change. Somebody takes some step forward and take the same step backward. His position has not changed. So how do you know the expected value now? So the logic is if the total that changed is 52 plus 32, which is 84. If non-hypothesis is true, half of it should be the one that hypothesis. The remaining half will be the one that came from non-hypothesis. That's why I say 52 expected value is 52 plus 32 over 2, making 42 for each of the cells. Can you see? So we now come to the formula of Zaman on the expected square over expected. You just put in, it give you 4.76. Now the degree of freedom, there's a way you calculate it. Put it there. Is look at it. K is the number of category of outcome. So this one, how many? 2. If it is 2, K minus 2 minus 2, 2 into 2 minus 1 over 2, it gives you 1. So the degree of freedom for this example now, for McNema is surely 1, because there are only 2 categories of outcome. So the chi-square, the critical value for the chi-square for the degree of 1, freedom of 1, is 3.841. So but this one we have calculated now is far, far above that. That should be significant. That shows that the change you have seen here is significant. The change you have seen now, if you look at it, before 60 were hypertensive, 140 were not hypertensive. After 40 were hypertensive, 60, 160 were not hypertensive. So you see 20 have changed. That 20 is significant. That's what it tells you. So then there's a way, another way, if you are using how to calculate it, very innovative way. Instead of all those things, just say B minus C, those discordant. You just say the difference between them, you square it over the addition and give you the same thing. Can you see? 52 minus 32 square over 52 plus 32. You give you the same thing, 4.4762. Degree of freedom is 1. Any question? Any question? So let's run this and we stop here. Let's run it. I think it's somebody to share. There's a data set at hypertension before and after. That's the name of the data set. That's what we're going to use so we can stop. Hypertension before and after. So by Monday, we treat McNema Bowker because now it's more elaborate. Cannot start it again now. So it will be confusing. So who is sharing?
I don't understand.
Okay, share. Hypertension before and after. Yes. Oh, yeah, I see good. . Yes, thank you. So it's very simple. Just go to analyze, cross-tab, and descriptive statistic, cross-tab. Go to analyze, descriptive statistic, cross-tab. So before should be on the row, pull before on the row. After column. So go to statistics. You see, no chi-squares, McNemar, you see McNemar. Down on the, after kappa and risk here. Click OK.
Continue.
And continue, yes. Okay. So share the output. You can't see the output. Stop sharing this and share the output. Yes. You see the same thing, the way the arrangement we, so you can see the chi-square, McNemar chi-square. But you know the funniest thing, you won't see, there's no software that's ever calculated. It looks simple, but the software cannot calculate McNemar, but it will give you the p-value. But we use hand to calculate it, and we cannot calculate the p-value. Can you see now? So that McNemar, you see that the value is not there, but the p-value is there. It's you that will put the value, and it's very simple. You don't need to go long way. The B minus C square over B plus C. That's all. This quadrant you're looking at, the two value, this difference between them minus the square. Either you even minus smaller one from bigger or bigger one. You know, when something is square, you remove the negativity. So when you minus, you square, you now divide by the addition of the two. Give you the maximum square. And this is the p value. Any question? We have 12 minutes more. Any question?
So you said to get the value, it is B. Is it from this?
The value is we have 52 minus 32 square over 52 plus 32.
Okay.
We are talking of the, it's only two cells you are looking at. The one that are discordant. Discordant are the one that either no, yes, yes, no. The one that are yes, yes, and no, no, they are concordant. They don't, for those ones did not change. So the people that were hypertensive before remain hypertensive. The people that are not hypertensive remain all hypertensive. They don't care about them. It's only the one that change. Yes, no, no, yes. So those are the one. You see, you remove, they are different, 52 minus 32 square over 52 plus 32. That is the difference between them square over addition of them. Give you the maximum square. It's very simple. So you calculate it with hand. You cannot know the p-value, just like normally you cannot calculate p-value for anything anyway with your hand. You can only look, okay, this is the critical value, this one is more, but the machine still calculate p-value for you. You calculate this thing yourself with your hand. Any question? Any question? So it's very simple. Okay, good night, everyone. So on Monday, no lecture tomorrow, Sunday. On Monday, we continue. We'll continue with chi-square. I think we'll finish with chi-square. That is the one that remains in McNemar Parker. That's what remains. So, any question? No question. Good night. So,
Thank you, sir. Good night, sir.